In the last class, we discussed about vibration monitoring, and then I focused my attention mostly on vibration monitoring by accelerometers, and then introduced you to how lasers could be used to measure from a distance without contacting the normal vibration, like in the case of the vibration from the compressor shell of a refrigerator, or rotational measurements, for example, using a rotational laser vibrometer, wherein we focused two beams to measure the fluctuation in the speed, which is nothing but the rotational velocities, and this fluctuation is at a frequency which is at the defect frequency of the system. But perhaps another very important parameter in any rotating machines to measure is actually its rotating speed. Because philosophically what happens, when we design a machine, I will come back to this example, where essentially we are dealing with machines where shafts are rotating, okay, and they are supported on bearings, right. Now, question is, when such shafts are supported on bearings and they are coupled to some other system which gives the power or some load. Now, if this, imagine this is designed to run at a constant speed omega. Imagine if this load torque for a moment varied. So, what is going to happen to the dynamics? Obviously, this load torque varies means either in terms of its amplitude or in terms of its omega. Okay. So, this is going to change the rotational speed and also the vibrations. So, once there is a change in the rotational speed, it gives clue as to what is the cause behind this change. That is one. So, one is measuring the absolute rotational speed or mean rotational speed. And next is change in the rotational speed. First, we will focus on mean rotational speed or the constant rotational speed. Why this is important? Because there is something called what is known as the forcing frequencies. As you know, for any system, now if I write it in the rotational domain, some it theta dot plus ct theta dot plus kt theta is equal to some load torque TL, which is a function of omega. Obviously, this theta etc. will respond at omega. So, this is my forcing frequency. And the response will be at the function of the forcing frequency. For example, a shaft is rotating at say 1200 RPM. So, what is the forcing frequency? Nothing but 1200 by 60, 20 hertz. This is my forcing frequency. Now, imagine this shaft had a fan or an impeller. Okay. Maybe I will draw the cross section here. It had an impeller, maybe with five vanes. Okay. some impeller. So, imagine if there was some fluid which was going on to the system. So, you see every time this fluid, in every rotation of the shaft, the fluid is getting obstructed 5 times. So, the fluid is getting chopped. If it was a blower, if we had vanes, the air would have been chopped. So, this is what is known as the vane pass frequency or the blade pass frequency. This is nothing but number of vanes or blades times the rotational speed. So, even if the shaft was rotating at constant omega, I will have a rotational speed, sometimes which you relate in vibration monitoring as 1x, and then there will be multiples if there are. So, 1x times n, okay, number of, so 5x, if there are 5 vanes, I will have a strong forcing frequency at 5x hertz and so on. So, this is how for a constant speed machines we need to measure the rotational speed. Now, what are the available transducers for rotational speed? So, you understand the significance of measuring rotational speed, because in a system when I am monitoring the vibrations, you all know by now that if I have a machine, if I put a transducer to measure the vibration, and if I do an FFT of it, fast Fourier transform, I will see certain peaks. Okay. So, this could be 1x, this could be 5x. So, you see this x is related to the rotational speed if there is a shaft here. So, when I am doing a fault diagnosis, I will be looking for 1x and 5x frequencies in my measured spectrum. So, for this frequencies to be known, I need to know what the rotational speed is, even the mean rotational speeds. Now, the way to measure it very cheaply, what we can do is, if I have a system like this, see every shaft they have a keyway. So, if I put a key here and I put a pickup, a reluctance type electromagnetic pickup, of course, there is a casing and all that. So, this is a reluctance pickup. So, what happens if the shaft is rotating? Each time the key comes below this reluctance pickup, the voltage, the gap is going to change. So, there will be a change in the voltage. So, what is going to happen if I look just in time domain, if I look at the voltage coming from this reluctance pickup, I would get peaks like this. Okay. And the interval between two consecutive peaks is nothing but the time period of rotation, time period of one rotation of the shaft. So, what is this? Essentially, this is a very small electromagnet. Of course, this has to be iron, this has to be okay, which is influenced by magnets or electromagnetic forces. So, what happens if I measure such a stream, and there is no power required. You can see how easily just by putting an electromagnet just close to a shaft, and every time there is a protrusion in the shaft because of the keyway. This is the key. This red one is the key. Every rotation I am going to get a pulse, and the distance between these two pulses, the time period, I can take for a longer time and then measure these pulses over a given period of time and come up with the mean speed. Okay. And this can be directly connected to a frequency counter. Nowadays, this is nothing but a frequency counter. So, this is, and these are very robust. So, in every industrial environment, such frequency counter based reluctance type pickups are used to measure the mean rotational speed. Okay. But we will see scenarios when there is a momentarily change in the load, even within one rotation there is a speed change. Okay. We will talk about that later on. So, this is some of the trade names of this reluctant pickup. One is what is known as a key phaser. Okay. There is a company who deal with these key phasers, okay, and they have named it. All are required if there is an electromagnet here. Okay. Some of them also have a capacitance probe. So, because if the gap changes, the capacitance would also change. So, such capacitive transducers are also used. Reluctance type transducers. But obviously, I mean, in many scenarios I have seen, when you go to the industry, if things are happening very slowly, okay, like the pendulum, you can measure the frequency just by measuring the time period, counting the time period. I have been to plants where a periodic tick noise occurs. So, sometimes this could be because of some phenomena happening. So, I just measure looking at my watch how much time it has taken between few ticks. So, we can find out the frequency of that event. But these are only good for very slow speed measurements. When we have high speed measurement, because these pickups also have their frequency limitations. Sometimes I also indirectly, you will see when we measure vibrations, the piezoelectric accelerometer which you put, if you are measuring the vibration spectrum, something like this, maybe even in 1x it will shoot up, and that would be due to the rotational speed. Okay. Just by measuring the vibration, you can find out the rotational speed. Of course, all these rotational speeds, some are the contact type. Okay. And this would be loading this system, but then contact type, you are measuring something, okay, like a tachometer or a tacho generator. For example, I have a very large turbine. Okay, I could put the reluctant type pickup, but sometimes momentarily offline one wants to measure the speed of a motor, electrical motor. The technician usually puts a tachometer, and where it is just an offline once time measurements, but it is mostly this non-contact type speed measurements. The previous two which we talked about, then we have a lot of this optical based measurements, like we could have used the rotational laser vibrometer, but they are very costly and rather okay. But then you can use the optical encoders, and of course, you have the optical phototach. or we also have what is known as the stroboscope. So, depending on what kind of instrument you are going to measure, on what is the severity and frequency range and so on, but I have still not told you that how to measure the change in rotational speed, momentarily change in rotational speed. In a very small time. What is known as the fluctuation in the rotational speed. I can use rotational laser vibrometer, I can use optical encoders, okay, and these sometimes could be used to find out the mean speeds using a non-contacting type. So, this is a view of an optical tacho probe or a photo tach. What happens? All we do, if a shaft is rotating, we shine a light. Okay. As you know, the light speed is very, very high, 310⁸ meters per second. Okay. So, almost instantaneously you will get a reflection back. Okay. And if I have on the shaft, if I put a reflective tape, so immediately instead of a reluctance type pickup where we looked into the magnetic field, here it is just again I will get a voltage pulse, but this is due to the optical effect. Some voltage. Again, by measuring the time difference, I can measure the speed at which this is rotating. Okay. But then there are scenarios, and of course, where I had perhaps given this to you earlier also, in a system wherein one set of pulleys are driven by a belt. A good example is the crankshaft, alternator, AC compressor of an automobile. If everybody is rotating and one is powering, maybe this is the crankshaft. Okay. And this is an alternator, and this could be your maybe your coolant pump. And of course, there will be few like the AC compressor, etc., etc., but just for the sake of discussion I am doing this. Now, imagine all of them are must have the same linear speed, because there is a belt which is going around. Of course, and depending on the RPM and the diameter, these omegas could be changing. Now, if there is a slippage of the belt, okay, and if I put a light here, flash a light onto this entire thing, okay, if I flash the light onto this at a frequency related to what is the speed, and if they are all running at a constant speed, they will, if the flash light frequency matches to the frequencies of rotation of this, they would appear to me as stationary, and this is the stroboscopic effect. Okay. So, there is a stroboscope wherein actually is nothing but a arrangement where we have a high flashing, earlier they used to have a high intensity krypton lamp. Of course, nowadays we have the LED lamps. So, this is flashed onto a surface wherein I have an oscillator. Of course, it will have a power supply and so on. So, I can vary the frequency of the light, vary frequency of the light. I don't know, many of you would have gone to discos, if you have seen people dancing around, and if you flash a light onto them, they will appear to you to be static. In fact, photographers use this technique to image systems which are moving at very high speeds, and you can get a stationary image. Okay. So, if it is flashed onto this light. So, how does stroboscope, other than measuring the speed of the system, help us diagnose the fault? Is for the fact that, imagine if one of them was not running at a constant speed, or the belt was slipping, belt slippage. So, then if I flash the light, what would happen is this belt would appear to slide over the surface. Okay. And so, by stroboscopic arrangement, I can find out the rotational speed of such systems and find out the slips in defective systems. Okay. But another important thing is what is known as this optical encoder. So, you see, you are getting a feeling that without even monitoring vibrations, just by carefully measuring the rotational speed of systems which are moving at a constant speed, if there is a fluctuation in speed, we can get some clue as to the condition of this machine, right. And if I talk about optical encoders, see, optical encoders are nothing but a disc, okay, which have slots on the periphery. I am not drawing all the slots, but all around they are. So, this could given as 1000 slots per revolution. That means, and now if I have an arrangement wherein I shine a light source at one end, and I have a detector, photo detector at the other end. So, what happens in one rotation? Okay, you see, in the case of the reluctance type pickup or the photo tag type pickup, I got 1 pulse per revolution of the shaft. Here, what I am going to get is, I will get pulse stream of how many? 1000 pulses per revolution. Okay, this is still in time domain. So, this is some voltage, usually 5 volts. Okay. So, 0 to 5 volts. So, I need to have a light source, and this optical photo tag obviously is connected to the shaft which is rotating, and then I will put a photo detector, and this is housed. In fact, in some of the earlier slides you had seen the image of such a optical encoder, and we will get this pulse, of course, because it is 1000 pulses per revolution. And even if the machine was running at very, very high speeds, even in few seconds you will get so many pulses. So, you are basically getting a pulse train. So, from this pulse train, the average, and each one of them is a time period. This is, I am denoting purposefully by small t, where 1000 such small t's would make up one time taken for one revolution or one rotation of that disk. But then there are signal processing algorithms, or let me tell you why, what happens. So, imagine if this pulse train, if I look at a very magnified view here, it may so happen even in one duration the spacing would change. Okay. The amplitudes are same. So, this becomes, in other words, a frequency modulated signal, and by analyzing this with a method called the Hilbert transform, which we have studied earlier, I can find out what is known as the instantaneous angular speed of the shaft. Okay. Excuse me. Now, the question is why this time changed. So, there is a fluctuation in the rotational speed. So, today the state of the art is people use optical encoder or encoders. Basically, if you think of this, every machine, be it a lathe machine, be it a nice electrical motor, people have optical encoders for the feedback circuit to measure the rotational speed and to maintain that rotational speed through a control mechanism. But imagine if this rotational speed pulse stream was recorded pulse stream was recorded, and we did an in situ analysis of this. We could find out the instantaneous angular speed, and later on you will see these time versus the IAS, instantaneous angular speed. You will see these variations could be very less, even from 0 to 5 RPM. You will see maybe in some frequencies these could be F1, F2, F3, these could be defect frequencies. And today this is the state of the art in CBM, that just by measuring the instantaneous angular speed through very cheap rotary optical encoders, we can also find out the defect frequencies or as to what is wrong in the system. And these could now be used with signal processing techniques like Hilbert transform, which we had discussed earlier, and I had given you some examples also. I can find out the defects in machines. Okay. And only catch here is I need to have a high sampling data acquisition device. So, such systems are in place, and we can find out the rotational speed. So, in summary, we discussed about both the mean speed measurement transducers for rotational speed, like the reluctance type pickup, the capacitive type pickup, the phototach, Stoboscope, and of course, to find out, of course, you can also use the rotational laser vibrometer. But nowadays the trend has been to find out the fault frequencies because of the instantaneous angular speed, and that can be measured also by an optical encoder or even a rotational laser vibrometer. And these techniques, so you see, without even using vibration, we can monitor the speed, fluctuation in speed, and then try to diagnose and find out the faults in machines. This is what the new technology is going to be, so on. Okay. So, more of these you can find in my book. Thank you.